morning everybody. Today we would be starting a tutorial on decoders and multiplexers. So we will discuss few problems on decoders and multiplexers. Okay, and this first question was about hazard, because this was also covered in the theory class. So if a circuit is given like this, okay, and it is asked, okay, to identify if there is an hazard, either hazard 1 or 0, okay, to eliminate it, then our approach should be to first make a K-map. Okay, only seeing a K-map we'll be able to identify whether there is an static 1 or static 0 hazard. And there could be anything, either it could be static 1 hazard here, or there could be static 0 hazard. So we make a K-map. Okay, so here in the original expression you had P R dash, and then the implementation P R dash and Q R. So we have to make the groupings accordingly first and see what is the problem with that. So this red line which is shown is QR, and the blue box which is shown here is PR dash, right? So you will find there is one static 1 hazard out here in this, right? Because there are two adjacent boxes, two adjacent ones which are not covered. So we need to make this gate also to avoid a static 1 0. Is it clear to everybody? What would be the approach like? Anybody? Yes or no? Can you say?
Sir?
Yeah. So whatever be the case,
Sir,
yeah,
static zero hazard will come when we are taking the max terms.
yeah, when we are taking the max terms. Okay. In that case also, in this case also there could be a static hazard, because you make one circle out here, and if you take these two out, okay, another circle, and then try to implement using max terms, okay, with NOR implementation, you will get a static hazard. So there should be one which is connecting these two also, correct? Normally if you take this dash and this dash, okay, can somebody say what would be that expression, this and this in a max term? This
P plus R.
it will be
P plus R.
P, yeah, it will be P plus R, and understood, it is because it is 0 0 here, P, and R also remains 0, so it becomes, since it is an inverted logic, otherwise for a NAND implementation it would have been P dash R dash. Now it will become P plus R. And what about this?
Q R dash. Q plus R dash.
It would be these two, yeah, Q plus R dash. Okay, so that would give a static 0 hazard. Okay, if you try to implement that, so you need to put these two also together. Okay, this will give you an additional term. Okay, this two will give a term which will be P plus Q, right? If you try to club these two boxes, it will be P plus Q. So that is how you find out what are the static zeros and static 1 hazards. Okay, so this is how after having inserted this additional green box, also you have an additional gate. So this will be an hazard free. Okay, so the penalty what we have to give here is, the penalty is an additional hardware. So if you are trying to make an hazard free circuit for any purpose, then the penalty will be additional hardware. Okay, this is the minimized hardware, this is the hazard free hardware where you have an additional hardware requirement. Okay, then this is pretty simple. Whenever we go to make an function using 3 to 8 binary decoder, right? What is that we got to do? We just have to club all the outputs right? Whatever is specific. Like this is actually, if you see, when we give 000 input, y0 goes high. So that is as good as a min term. This means this is a min term. Okay. So y1 is a min term, because when we give 001, y1 goes high. So these are all actually, you can call them as min terms. So a function is on what? A function is just a collection of the required min terms. So simply we can connect the required min terms and put a OR gate. Okay. Can somebody tell you, there will be some encoders which will be active low. Okay, active low means the output would be 0 for that particular combination. Okay, if you give 000, otherwise the normally it will all be 1. For 0000 it will be 0 here. Okay. Okay, what is the question? Yeah. Okay, this is just an W1, W2, W3. It's given the other way around. W0 is actually MSB, LSB. Okay, in within a chip, if you see, W0 is MSB, LSB, then W2 is the MSB. Here, if you see in the function, W1 is here in the MSB position. So that is the reason we write W1, W2, W3 here. Is it clear, Viraj? Yeah. Okay. So yeah, you have to be careful with this also, right? If this combination is wrong, then your answer will be wrong. So you got to be careful with this. Okay. Another variation to this problem could be when you are writing a gate or other thing, there could be an active low decoder also. Active low decoder means whenever you give say 000 here, normally everything will be 1. Only the bit which corresponds to the input will go low. So in that case, what kind of gate will you use? This is an OR gate, right? If it is active low, right? What kind of gate?
We can use an AND gate, so there.
NAND gate?
AND gate, so.
Yeah. If you use an AND gate at any given point, 1 will be 0, right?
Oh, yes, sir. Yes, sir. So probably then we can't use it.
Then what do we use? If you have active zeros going, what is the gate? NOR. If you use like you said, if you use NAND gate, I think that should do, right? Because we are taking only the min terms. So any time any 0 comes, the output should go high. Okay. At any given time, if any input comes as 0, right? If all are ones, then it should be 0. If at any given time, if any one of the inputs is 0, then it should go high. So NAND gate should do, isn't it? Anybody?
Yes, sir.
Yes, sir.
Yeah. So so like somebody prompted, it should be a NAND gate. Okay. So be careful in your exam. So you might have some variations of these kind of questions. Even gate also you will have these kind of questions generally. So they'll be they'll say active low, or they'll mix up these variables inside. So you got to be careful with these two things. Okay, the variables, which is the order in which these variables are put here, and the gates which we are going to use here. Okay. So implement full adder. Now we want to implement a full adder. Full adder implementation we have seen with XOR gates and all in our lab. So let's now try and make it a full adder using an 2 to 4 decoder. Okay, I think 3 to 8 decoder we require. So this is just to revise what a decoder looks like. It was covered in the class. Okay, what if it is 0 0, what happens? Okay, d0 line goes high, this line goes high, this is corresponding to d0, right? And when the enable line is 0, all the 4 AND gates have been disabled here. If you see, when it is 0 0, all the lines irrespective of A and B, all the 4 lines will be disabled. Okay, so this enable line is very important when we make big multiplexers out of small multiplexers. So the enable line will be used there to choose which output we require, right? So you have 0 0. So for 0 0 you have d0 line going high. For 0 1 you have d1 line going high. For 1 0 d2 line and d3 line. These are the 4 lines which are going to go high one by one. Is this aspect clear? Okay, how this works? So those who are someone from L2 or those who are not attended the theory class, operation of decoder is clear? Anybody? Yes or no?
Sir, in this diagram, the enable pin acts as a carry input or just an enable pin?
No, this is just a 2 to 4 decoder. If enable is 0 and enable is 1, it enables this decoder.
Okay, so it is not a full adder.
No, it's not. We have not yet discussed the full adder.
Okay, sir.
Okay, so this is going to be there. So now how to implement it? There are, for a full adder there are 3 inputs, right? So we group all the 3 inputs, right? And then we write the sum, where all sum has to be high. Okay, so here if you see there is only one 1, so sum will be high. Here also there is one, there are 2 ones here, so it is 0 and a carry high. So here there is one, only one. Here again there are 2 ones, so it is 0 and 1. 1 1 0, again 2 ones, so 0 1. In the last case you have 3 ones. So if you have 3 ones, it will be 1 here and a carry 1 here. So how to implement sum and carry? We just pick up those corresponding wherever for whatever min terms you have sum as going high, you put an OR gate, and wherever there is an carry, you put a carry gate. Okay. So Gandhi, you see, there's no requirement of an extra OR gate. Yeah, we need an extra OR gate, like you said. We just require an extra OR gate for, so you can generate multiple functions, not necessarily only sum and carry. If you have an 3 inputs like this and a decoder, so whatever functions, you can have infinite number of functions. You just have to collect the corresponding number of min terms, whatever is possible. Not infinite, it will be whatever permutation or combination of this 0 to 7, whatever combinations you want, you will be able to get the output. Okay, in this case it is sum and carry, so the necessary min terms have been clubbed together. Is it okay?
Excuse me, sir.
Yeah, tell me.
Sir, here we are adding the 3 bits X, Y, and Z.
Yeah.
Okay, so like in norm, if we don't use a 3 to 8 decoder, we can like just implement it using simple AND and OR gates, right? So would this implementation be more costly or cheaper, sir, in like hardware terms?
No, it will be this will require a lot of hardware inside this, right? So if you see what is there inside this is 3 to 8, lot of hardware will be required in this.
Yes, sir. So, and in terms of like speed and all, would there be a big variation as such, because there are more gates, so we can assume it will be slower?
No. See, what happens is, suppose like you take an full adder is a customized chip, okay, but whereas multiplexers and deplexers are an general block, you can use for any kind of applications. Okay, so sometimes if you have say a few decoders and on a chip for a testing purpose, you can test if you have made some logic, you can test the functionality of your logic by using these, right? So generally we wouldn't use this to implement an full adder. Okay, they are custom design. These are all generalized. Like FPGA will not be an ideal answer, but in an FPGA, what is there? It is full of NAND gates, full of NAND gates. Okay, and there will be some blocks like this. So FPGA is not specific to any requirement. So as per your program, it will pick up the blocks and give you an output. Okay, so that output is good enough for testing your some, maybe you have made a good new architecture, so for testing that it is okay. But after the testing and all, everything is done, you want to make an actual chip for an application, and then we'll go for a custom design. In the custom design, all these blocks will be replaced by the optimized gates. Okay, so when you are working at a high level, those times a few of the generalized blocks will be used.
Understood, sir. Thank you.
Okay.
Sir, could you show the previous slide?
Yeah, this.
Yes, sir. So in this one, shouldn't the second one be A dash B?
No, they have taken A as MSB here. That is why.
Okay, sir, fine.
Okay. Okay. Now this is one to implement 8 into 1 mux. Okay. So it is again, you make a truth table, right? So this is also we know how a mux works. I have explained it in the theory class. So here also what we are going to do is, there are several inputs available here. Okay, all the possible combinations is written here corresponding to the min terms, and what is the value of f, that we are writing from the expression. Okay, and then we are going to map the value of f into each one of these inputs. Okay, so this will, like if it is 0 0 0, this line will be enabled. So what is the value of f there? It is 0. So that 0 will be reflected outside. Similarly, if you have 0 0 1, this line will be activated. It will be connected to f. So you have 0 being transmitted there. For 0 1 0, okay, the value of the function should be 1. So here it is 1. So this will get reflected outside, right? So similarly for all the min terms. Now is it okay? So any function can be implemented with the help of mux like this. Is it clear to everybody? Anybody has got any doubt? Yeah, okay. So is it necessary to make a truth table like this? Is there any other method? I gave a hint in the theory class.
So we can take like 1 0 1 and just add it using the expression there, like x dash y z dash, and then write the corresponding output.
Yeah.
What we get.
Yeah, correct. So what we can do is, we don't have to make this in a truth table also. If you put x is equal to 0, y is equal to 0, z is equal to 0 in this expression, right? What happens is, see, there is a y here, so this becomes 0. There is an x here, it becomes 0, and there is x, so this becomes 0, right? If you take then 0 0 1, right? If you put 0 0 1 also, y is here, x is here, x is here, so this is 0. If you take the third condition, which is 0 1 0, so this is going to be 1, right? Because y is 1, this is 0, and this is 0. So so we don't have to bother about this. There is going to be 1, so we put a 1 here, right? So even without this table also, we can solve these kind of questions. Okay, so if you're going for a gate or something, time becomes an issue. So in those conditions you can just verify these results, right? So okay, so what about this? Here we are taking only two variables, okay, x and y, and we are going to use z also as an input. So in that case we will make a will make a separation like 0 for 0 conditions. This is x0 y0. So this is the condition. So now we have to express f in terms of z, right? So what is it? Now how can we express f in terms of z here? What is f for these two conditions? Yeah, it is 0. So we just put a 0 here. Okay, so the next set of conditions is x0 and y1, x0 and y1. So here we have, right, this what is the relation between f and z here in this in these conditions? It is, yeah, it is z bar. So you put z, you put an inverter, and then you put it 1 here. Okay, then again you take one more condition of x1 and y bar. Okay, in this what is the relation between z and f? Anybody? Yeah, like Sujit said, it is directly. So you put z there, and in the third condition, right, if you put x equal to 1, y equal to 1, the relation is again z bar, right? The between y and f, the relation is inverted, so you put an z bar. Okay, is it clear to everybody? Is it clear? Can you say yes or no? Anybody has got any doubt in this? Okay, now can we is this again truth table required? Can we do without this truth table? Anybody can you speak in the mic? No issues.
Yes, sir.
Is the truth table required, or can we do without the truth table?
We can do without it.
Yeah, because without the truth table, again it is simple. Okay, you can apply 0 0 here. So once you apply 0 0 here, you will find that it is all zeros. For the case of 0 1, if you apply 0 1 here, what happens? Okay, 0 0 1. So z we have to keep it as it is. Okay, so if you kept 0 1, this vanish and z dash will remain here. Here also this will vanish, but only z dash will be available here. So you put z dash. Okay, so accordingly we will get in terms of z. Okay, is it clear? Okay, it could be a 4 variable this thing also, and then if you are using 2 variables, okay, then also 2 variables will remain here. Okay, so whatever is that expression, you need to put to the corresponding inputs. Is this aspect clear? If there are how to go about designing a 4x1 mux? Anybody? I think with that we have finished today's tutorial.